So we're going to talk about question 5, collisions, the B part, which refers to oblique collisions. Oblique collisions are collisions where the balls do not collide when they've been travelling along their line of centres. The line of centres will be the line between the two centres when they collide. In this situation, they're going to be travelling at particular angles. Okay, so the rules are basically the first thing you do is you resolve the velocities into components parallel to the line of centres and perpendicular. So if we call that theta, we call that alpha. That's u1 cos theta, u1 sine theta, u1, u2 cosine alpha, u2 sine alpha. So the first rule is that the only change that occurs in the velocity is the change in the direction that is along the line of centres. Okay, that means that for the velocities afterwards, okay, I didn't leave myself a lot of room here. For the velocities afterwards, you have a component in this direction that is no different to the component in this direction. So this remains as u1 sine theta. Okay, this component also remains as u2 sine alpha. Okay, I hope you can read that. Now, in this direction, we'll call the velocity x and the velocity y as we have done before. Okay, hopefully you can see that in the diagram now, it's not that clear. So, our principle of conservation of momentum will still apply and our Newton's experimental law, but we will only use the principle of conservation of momentum for the velocities in the direction parallel to the line of centres. Okay, so mass, if we call that m1 and that m2, that means m1 times u1 cosine theta plus m2 times u2 cosine alpha. The momentums beforehand in the direction along the line of centres is equal to the momentums afterwards in the direction along the line of centres. Okay, and then we have Newton's experimental law, which also applies in the direction along the line of centres. X minus y is equal to minus e times u1 cosine theta minus u2 cosine alpha. Okay, so that's the basic rule for part B's. Okay, so now I'm going to do an example from the book. I'm going to do the example on page 118, and I think it's example 7.6. So example 7.6, page 118. Two spheres collide. This one is of mass 2 kilograms, this one is of mass 1. The velocity of this one, this is the line of centres, is 2i plus 3j, where I is along the line of centres. Okay, so I won't put in the I, but it's 2 in the direction along the line of centres and then 3 perpendicular to that. The velocity of the other one is minus 3. I could draw it that way as plus 3, but it's easier to put it in this way. Minus 3 in the I direction and 1 in the j direction. Immediately applying the rule that I've just pointed out, no change in the velocities perpendicular to the line of centres. Okay, now that's similar to when you have, remember when we had a ball or whatever and we had it was landing and it would have a velocity v, which we would resolve into a components perpendicular to the plane and parallel to the plane of where the ball lands. Remember what happens. It bounces back up, and if this was its v in the y direction and this was its v in the x direction, its new velocity after bouncing is e times vy in the upward direction, but its vx stays exactly the same. You do not multiply the vx by e. Now, several of you did that in the mock exam. So that's a similar idea. The only change occurs in the line sort of perpendicular to the collision. Okay, so if you think about it, these are colliding. Okay, so at the point of collision, it's only the change occurring in the direction perpendicular. All right, so that's why the only change occurs along the line of centers. So they stay the same. We now call this velocity x and this velocity y. And we use our principle of conservation of momentum, which states that 2x, I'll start with the momentum before, 2 times 2 plus 1 times minus 3 is equal to 2 times x plus 1 times y. Okay, that's minus 3 and 2 is 4, so we have 2x plus y is equal to 4 take away 3, which is 1. That's our first equation. The second equation, Newton's experimental law, x minus y is equal to minus e. Now you're given in the question that e is 4 over 5. So it's equal to minus e times that minus that velocity is minus 4 over 5 times this velocity, take away this. So 2 take away minus 3. 2 take away minus 3 is 2 plus 3. 2 plus 3 is 5. The 5 and the 5 divide out, so we have x minus y is equal to minus 4. Okay? We now use those two equations and we solve them. So if we add those two immediately, we have 2x plus y equals 1 and x minus y equals minus 4. Adding together, we get 3x is equal to minus 3, x is equal to minus 1. That means our x here is minus 1. For our y, again, you have the choice. You can put the minus 1 back in, which is dead straightforward here. But your other option is to put, when this gets more difficult and you may have fractions for your x, then you can also just decide to cancel out the x's and figure out what the y is. So you would have 2x plus y equals 1 and minus 2x plus 2y is equal to 8. Okay, all I did was multiply that one by 2. Adding together gives you 3y equals 9, y is equal to 3. Now I know that's an overkill in this situation. It's probably easier to put the minus 1 in, but in other situations where you have fractions or e's in your answer, it's better to just solve again, eliminating the other variable. So y is 3. So now we know that y is 3. So we have found the velocities afterwards. You may be asked to talk about the actual magnitude and direction. So you guys should be well able to state what the magnitude and the direction of these are. The magnitude of that is the square root of 3 squared by Pythagoras plus minus 1 squared. So that is the square root of 10. Okay, also to note that that's a minus 1, so it's actually in this direction it's plus 1, and that's the 3. This is the square root of 10, and then this angle is, the tan of this angle is 3 over 1. So theta is the tan inverse of 3. So we can say the velocity of that is the magnitude is the square root of 10 at an angle tan inverse 3 north of west. Okay, that's the angle north of west. Obviously, you'd have to look up the tan inverse of 3. Okay, and in a similar way, you would say that y, this one, and again, if you look actually, by coincidence, 3 squared plus 1 squared, so that's the square root of 10, and this time it would be at an angle alpha, where alpha is alpha degrees north of east, and alpha will be the tan inverse of 1 over 3, so the tan inverse of a third. Okay, now the next part of the question says the loss in kinetic energy. Now when you're looking at the loss in kinetic energy, you must look at the kinetic energy of everything. You include the velocities in the two directions. So let's have a look at the kinetic energy here. So the magnitude of this would be 3 squared plus 2 squared, so that's the square root of 13. And the magnitude of this one is 3 squared plus 1 squared, so that's the square root of 10. So to look at the change in kinetic energy, you need to look at the kinetic energy before. The loss in kinetic energy will be the kinetic energy before minus the kinetic energy after. Remember that the formula for kinetic energy is a half mv squared. So the kinetic energy before is 1/2 times 2 times the square root of 13 squared plus 1/2 times 1 times the square root of 10 squared. That's the kinetic energy before, and we have to subtract out, so that's the kinetic energy before. The kinetic energy after is 1/2 times 2 times the square root of 10 squared, 1/2 mv squared, plus 1/2 times 1 times the square root of 10 squared. So that is 10 plus 5, which is 15 for the afterwards, and joules because it's energy. What about before? 1/2 of 2 is 1, 13, the square root of 13 squared is 13, so that's 13 plus, and again 1/2 of the square root of 10 squared, the square root of 10 squared is 10, and 1/2 of that is 5, which is 18 joules. So the loss in kinetic energy is 18 joules, take away 15 joules, which is 3 joules. Okay. The next bit refers to the loss, or refers to the impulse. Okay. Now remember what we said before. The impulse is the loss in momentum, and it's just an impulse to one sphere and an impulse to another sphere. Okay, so the impulse, the definition of the impulse, I think I've told you this before anyway, the impulse is mv minus mu for a particular sphere. Okay, so mass times velocity before or after minus mass times velocity before. Okay, so if we have a look for this sphere here, okay, then the mass times velocity afterwards is 2 times, and its velocity is minus 1I plus 3j, and that's mv. mu is m times 2I plus 3j. Okay, now what's mv minus mu? Well, that is minus 2I plus 6j. Take away, we're subtracting this, and that is 4I plus 6j. So 2I take away 4I leaves you with, minus 2I take away 4I leaves you with minus 6I. And the 2 times the 3, the 6j take away 6j is 0. Okay. Now again, you could have got that by literally, because we know that these don't change, you could have just said 2 times minus 1 take away 2 times 2. Okay. Because we know already that the j bits are going to cancel out because they haven't changed. So in this situation, we won't bother looking at the j bits. If we just look at where the change in momentum occurs, it's mass times velocity, which is 1 times 3. That's mv. Take away mu, which is take away minus 3. So that is 3 plus 3, which is 6. Now, note that the change, I'll go out of the way for the shadow, we note that this one's impulse is minus 6I, this one's impulse is plus 6I. That makes sense because then the total change in momentum, that's the change in momentum for one sphere, that's the change for the other. When we add the two changes in momentum together, we get 0, which makes total sense from the point of view of the principle of conservation of momentum. Okay, and the last bit was the angle through which the heavier sphere is deflected. Okay, so if you remember, we already had worked out that this angle was the tan inverse. Now, remember, when we look at this afterwards, okay, I'm going to rub this out just to get it out of the way. What this actually is this is we know that this is now moving in this direction. Okay, so I won't call, that was our theta, and theta was the tan inverse of 3. All right. Oh, sorry, and the original, that was the original. We're actually only interested in that. That was 3. So this angle, we'll just call it omega just now, right? The angle that it was at going at beforehand, omega was the tan inverse of, the tan of omega is 3 over 2. 3 over 2. Okay? Now, theta is not the angle that this sphere was deflected through, because if you look at it with reference to the horizontal, this sphere went from omega, okay, which was somewhere here, all the way around to here. All right, so we need to find the angle that the sphere was deflected through. Now I need a calculator. Okay, so the tan inverse of 3, I just set it into degrees. Now, the tan inverse of 3 is 71.57 degrees. Okay, now that means this angle is 71.57, which would put this angle at 108.43. So this angle is the tan inverse of 3 over 2. So tan inverse of 3 over 2 is 56.3 degrees. So what we're saying is it was moving at 56.3 degrees to the horizontal. It's now moving at 108.43 degrees to the horizontal. So the change in the angle is it has been deflected through 52.12 degrees. Okay, so hopefully you can see that. Its new angle to the horizontal is 108. It was 56. Subtract the 2 to get 52.12. All right.